In today's discussion, we're going to be talking about bifurcation diagrams and how to read bifurcation diagrams. So let's start with a little bit of review about what a bifurcation diagram is. A bifurcation diagram helps us to capture the relationship between a model's parameters and a model's behavior. And when we say behavior, we really are talking about the equilibria of the system. We know from last week that the equilibria give us a sense of the long-term behavior of a system. If we pick any point in state space and we want to know where that point ends up, there's only a few possibilities. It either is going to flow into one of the stable equilibria, continue to flow away from an unstable equilibrium, or circle around one of the neutral or central equilibria. So the equilibria completely capture the behavior of the model. And our bifurcation diagram is going to allow us to study how different parameters of the model can affect the types, numbers, and locations of the equilibria. So let's look at an example. Let's look at the population model with the alley effect. Here the equation is x prime equals 0.1x times 1 minus x over k times x over a minus 1. And here we have two parameters. We have our state variable x, and then we have two additional letters or parameters coming into the model. We have k, a carrying capacity. This is the natural size of the population that the environment allows. And we have another parameter a, which is kind of a minimal viable population. Alley hypothesized that you need to have a certain number of individuals in a population, a minimal number, in order for that population to continue to be able to reproduce and support its numbers in the environment. And he added this term to the population model in order to enforce that. And when we're drawing a bifurcation diagram, we're asking, well, how do these parameters k and a affect the kind of equilibria that we see in this model, in this population model? And since it's kind of difficult to reason about both of them at the same time, we're specifically going to think about the relationship between k and a. Namely, how are things different when a is equal to k, less than k, or greater than k? And so we're going to end up drawing a bifurcation diagram where a, our parameter, is what we're going to be tracking on the x-axis. And so the values we really care about are k, and we're going to end up with a diagram that looks kind of like this. Give me 1 second to draw the diagram. So we end up with a picture that looks like this, where here our blue lines are representing the stable equilibria. Our dashed red line represents unstable equilibria. So how do we read this diagram? Well, if we pick any value of a, so I'm going to pick this value right here, maybe around k over 2. And I just restrict my focus to what's happening directly above this value of k. So in this little window that I'm drawing, then what I get out is itself a phase plot for the system with that value of a. So here I end up with 2 blue equilibria. And I have one red unstable equilibria. Here these are at values 0, k, and let's call this y. We know from last week that this is actually equal to k over 2. It's equal to that minimal viable population. Sorry for switching colors on you. But then we see that we're flowing into the stable equilibria and away from the unstable equilibria. So we end up with this phase plot. And this bifurcation diagram is really summarizing all of the possible phase plots. If we had picked a different A value, we would have gotten a different picture. So that's kind of cool. This bifurcation diagram with a pretty simple picture gives us a lot of information about the system. And now you might be asking, why is it called a bifurcation diagram? Well, this point here, where the behavior of the system changes, where either the count or the type of the equilibria are changing, this is called a bifurcation. And this specific type of bifurcation we see here is called a transcritical bifurcation. As we see that right here, there's only 2 equilibria in the system, as opposed to everywhere else where there's 3. There's a stable, and then an unstable, and then another stable above it. Here we have a different behavior, and we denote this by calling it a bifurcation. So in today's discussion, we're going to be talking about a different type of bifurcation we can see, called a pitchfork bifurcation. And we're going to see an example of a system where this kind of bifurcation shows up. Specifically, we're going to look at a group of people. Here we have a fixed number of people, M, with 2 possible opinions towards something. Maybe they have a positive opinion or a negative opinion. And we're going to study how these opinions change over time. So if we look at question A, we're modeling the system as one of these box and arrow diagrams, a compartmental model that we're used to. And we're using K1 to represent the rate of people changing from a negative to a positive opinion. And K2 is representing the rate of people changing from a positive to a negative opinion. And we see that both of these are per capita rates, which means that the number of people flowing from N to P is really K1 times the source of the arrow. So K1 times N. And on the bottom, the number of people switching from positive to negative is K2 times the source of the arrow, K2 times P. So if we write down our change equations, this is from a while ago, we're going to pick a box. So we'll pick the P box, and then P prime is going to be, well, it's going to be all the inflow arrows are going to be positive in the equation. So K1N, and the outflow arrow is going to be negative. So minus K2P. Same for the N change equation. N prime is equal to, we have our K2P inflow, and we have our K1N outflow. So those are our 2 equations. Now, just like we did down below with the alley effect, studying 2 quantities at the same time can be tricky. We need more dimensions. And so in order to reduce the dimensionality of the problem, in order to reduce the number of things that we have to track, we're going to define a new variable x, which is going to capture both the positive and negative opinions at the same time. And here's the definition. We have x equals p minus n over m. So it's a measure of how much more positive is the opinion than negative at a specific amount of time. And so let's kind of do some examples of this to wrap our head around it. When x equals 1, then, well, plugging in for x, we see that p minus n over m equals 1. Multiplying by m, we have p minus n equals m. Now we know that the total number of people, M, is going to be the number of people with a positive opinion plus the number of people with a negative opinion. m equals p plus n. And so if we add this to our equation, if we add these together, we see that 2p equals 2m, so p equals m. In this case, all m of the people have a positive opinion. If we look at x equals 0, then we have p minus n over m equals 0. Multiplying through by m again, we have p minus n equals 0, which tells us that p is equal to n. And since p plus n has to be m, then both p and n have to be m over 2. So x equals 0 is an even split between positive and negative opinion. Exactly half the people are positive and half the people are negative. And for x equals -1, same thing again, p minus n over m equals -1. Tells us that p minus n equals negative m. If we add our other equation, p plus n equals m to this, we get that 2p equals 0, so p equals 0. Now no one has a positive opinion, which means that everyone has a negative opinion. And we see that x equals 1 and x equals -1 are our two extremes. If we pick any x value in between -1 and +1, we're going to have some split between negative and positive. So here we see that x is in the range from -1 to +1. Okay, so now we've kind of set up our system. We've defined our state variable x. We've defined the behavior of the system. Now we want to wrap our heads around what are these K1 and K2 going to be? How are we going to define the rates of change in our model? And we're going to do this using an assumption of a bandwagon effect, which means that the more people that I see around me who have a positive opinion, the more likely it is that I'm going to switch my opinion to positive. And vice versa. The more people around me who have a negative opinion, the more likely I am to switch to have a negative opinion myself. And as you go through this paragraph, you'll see that we've defined a coefficient A. This is our parameter in our model, which is going to measure the strength of the bandwagon effect. So here, we see that our parameter is A, so in our bifurcation diagram, A is going to be along the x-axis, and our state variable is x, which is going to be on our y-axis. And this picture, right here, this kind of pitchfork-looking picture, is our bifurcation diagram. So now the next few questions are going to help us understand exactly what's going on in the diagram. For C, it says determine the number and stability of equilibrium points for A less than 1 and A greater than 1. So if we pick a specific value of A that's less than 1, so let's look right here in this purple region. We see that, well, inside of that purple band, there's one black equilibrium point. Here our black is going to be stable. So for A less than 1, we have one stable equilibrium point. I'm going to use EQ to abbreviate equilibria. And then if we look at a value of A greater than 1, so maybe right here, we see that now as we read from bottom to top, we hit a stable equilibria. Then at 0, we have an unstable. And then like above, we have another stable. So for A greater than 1, we have 3 equilibria, 2 stable, and 1 unstable. And now we said that the bifurcation is going to be the location where the nature of the equilibria shifts. So as we look at the bifurcation diagram, working our way from left to right, we know that all the way up until we get to 1, we always have 1 stable equilibria. And as soon as we're bigger than 1, now we have 3. That means that our bifurcation has to happen at 1. Here's our bifurcation. The location where the number and type of the equilibria splits. In this case, as A increases through 1, our one stable equilibrium, it becomes unstable as 2 stable equilibria kind of divide out of it. If we were to instead look at it for decreasing A, as I move A down closer to 1, these 3 equilibria, 2 stable and 1 unstable, are moving in closer together until they merge into a single stable equilibria at 1. Okay, let's take a look at question E. Now we're supposing that A is less than 1. We want to describe the long-term behavior of the system. So here again, we're looking in the purple band. We see that there's only 1 equilibria. So there's 1 equilibria at 0. From the diagram, since it's a black line, we know it's a stable equilibrium. So our phase portrait, our phase plot is going to look like this. So no matter where we are in the state space, no matter what the value of x is, we see that it's going to approach the stable equilibrium, at 0. So the long-term behavior of the system is that we tend toward 0 regardless of where we start. And in the language of this problem, we know that x equals 0 corresponds to an even split between positive and negative. So the long-term behavior is that there will be eventually an even split of opinion. In question F, we're looking at what happens for A greater than 1. So here we've got a phase portrait that looks like this. We have a stable equilibrium, then an unstable equilibrium, another stable. So our plot looks like this. And here our behavior is, well, if we started with more than, here this is at 0, if we started with more positive opinion, well then we're looking at the right half of the diagram. And here we see that there's 1 stable equilibrium over here and we're drawn into it. So we approach the positive equilibrium. So we end up with, eventually, we have opinion leaning positive. And if we start more negative opinion, then now we're looking at the left half of the diagram. We see that there's 1 stable equilibrium. Every point gets drawn into it. So we eventually have a negative leaning opinion. And this kind of makes sense. We said that A is representing the strength of a bandwagon effect, how likely other people's opinions are to influence mine. Well, when there's a low bandwagon effect, like in part E in the purple example, well, if I really don't care, then eventually everything's just going to kind of even out. While on the other hand, if I feel very strongly about how the people around me feel, well, if around me I see more positive people, then I'm more likely to tend positive, so the entire group is more likely to tend positive. On the other hand, if I see more negative opinion around me, I'm more likely to tend negative, which means the whole group is going to move negative. I see these two different behaviors depending on where we started. Let's take a look at question G. Suppose that A is large, we're looking at the orange case, A greater than 1, and that there's a perfect split in the opinion, x equals 0. Well, we see from the diagram that x equals 0 is an unstable equilibrium. So that means that if there's no fluctuations, I'm going to stay at having my perfect split at this unstable equilibrium. But what happens if there's a tiny fluctuation toward the negative opinion? Well, now, let's see. So here I am. I'm sitting right here in the bifurcation diagram. If I have a tiny movement toward the negative direction, towards a smaller x, well then I'm not going to be sucked back up toward the unstable equilibrium. The only way that this point can move is down to the negative stable equilibrium. So a tiny fluctuation will lead to me flowing into the negative equilibrium. So it leads to a greater occurrence of the negative opinion. I don't think occurrence is the right word. I think I should say prevalence. So that's an interesting thing. We think we're in a room, the opinion is perfectly split, but we feel really strongly that we want our opinion to match the other people in the room. So as soon as one person speaks up with their negative opinion, well then a lot of people are going to see, oh, well now the room is leaning negative. We should probably also adopt the negative opinion. And we see a big flow of people to the negative opinion in order to match the people around them. Okay, so here's our example of a bifurcation, and this, we called it the pitchfork bifurcation. For obvious reason, if we tilt it up on its side, it looks just like a pitchfork. Let's take a look at question 2. Here we're looking at another bifurcation diagram. This one, X is measuring a bass population in a lake, and R, our parameter, is the carbon input in the lake. So here's an example of using a bifurcation diagram in practice. Here we have some agency that wants to regulate the bass population in the lake. The thing that they have control of is the carbon input to the lake. And so they want to see how can they adjust the carbon input using this bifurcation diagram to see that they can achieve a certain bass population. Looking at question A, we say suppose the carbon level is R equals 55 and the bass density is 0.1. Okay, so for question A, let's make this orange in our diagram. So we're looking at R equals 55. So we're looking at this band. And we have that the bass density is 0.1, which means that we're hovering around this stable equilibrium at the bottom. We want to increase the bass population by introducing new bass into the lake. Our goal is to get a density of 0.6. So we'd like to move up to this stable equilibrium point. This is our target. To reach our goal, up to what density do we need to introduce bass from the bass farm? So let's go ahead and draw our phase portrait for the system at r equals 55. We see that we have a stable equilibrium at 0.1. We have an unstable at maybe around 0.15. We have another stable at around 0.25. We have an unstable around 0.4. A stable at 0.6. An unstable at 0.7. And then a stable around 0.9. And if we draw in all of our phase errors, we see that, well, the lowest value that we have that will eventually lead to flow up to 0.6 is right above 0.4. Anywhere below 0.4, we're either going to get attracted into the 0.1 equilibrium, or we're going to get attracted into the 0.25 equilibrium. At 0.4, that's an equilibrium point. It's unstable, but if we're exactly at 0.4, we would stay there forever, which means that we need to get the bass density here in order for it to eventually flow up to 0.6. And really specifically, we can introduce bass to anywhere in this 0.4 to 0.7 range. So in order to get it to flow into the 0.6, as long as it's within the range closest to that 0.6 stable equilibria in that interval, then the population will tend toward it. So we need x in the range from 0.4 to 0.7, non-inclusive. And our explanation of our reasoning is what I said. It's that in this interval, the closest stable equilibrium is x equals 0.6. Okay. Let's take a look at B. Now in B, we're assuming that we don't have control of the bass density. Instead, we have control of R, the carbon input. Let's make this our purple question. Initially, we have R equals 70 and X equals 0.05. So we're right here on the bifurcation diagram. How can we manipulate R to raise X to approximately 0.9? And how will X change during the manipulation? Okay, so we want to end up at around 0.9, which means we want to end up on this stable equilibria line. We want to end up somewhere here. And so the idea is we're going to adjust R a little bit. We're going to have the system flow to the closest stable equilibrium. Then we're going to adjust R a little more and flow to the closest stable equilibria. And we want to eventually flow up to this purple line that I drew in. Now we can see that this unstable equilibria line, this unstable equilibrium line here, until we can get above that dashed red line, we're always going to flow back downward towards those lower stable equilibria where the kind of loop is in the middle, which means we need to find a way to stably get above that line. And the only place we can do it is way down here. The only way is if I can move the system down here, jump up onto this stable equilibrium line, and then kind of ride it this way until I can get kind of over here where I can jump up to the line that I want. So let's write down the steps. First, I want to lower R to, well, it looks like this happens around 10, so I'm going to say 8. If I lower R to 8, then I'm moving this point all the way over here. And then at 8, I see that my phase plot looks like this. I have just a single stable equilibrium at 0.6, an unstable around 0.8-ish, and then a stable pretty close to 1. Right now I'm currently right here, and if I draw in my arrows, I see that that will cause the Bass density to approach 0.6, the stable equilibrium. So now my Bass density is 0.6. And now we said that I want to kind of ride up this middle stable equilibrium right here. I want to ride up this over to around 0.4 where it hits its peak. So step 2 is I want to slowly increase R to 40. And the word slowly is that if I were to jump too fast over, well then I'm going to cross over the dashed red unstable line and go back downward. So what I need to do is I need to raise R a little bit and have it reapproach the stable equilibrium. Raise R again a little bit and have it reapproach the stable equilibrium. And keep doing this, riding up the curve until I get here. And really, I can even just, instead of just going to 40, I can go to 45. And then here at 45, I see that, well, now I'm sitting around 0.8. I'm sitting around 0.8. My closest stable equilibrium is at 0.9, and I have an unstable equilibrium below me around 0.65, which means that once I get to 45, once I get to R equals 45, that will take me directly to the Bass density of 0.9 that I need. So this will get me to a Bass density of 0.9. I think that's a kind of tricky question. Here we had to do it in multiple steps, but we were able to kind of use the idea that stable equilibria draw in the nearby points in order to get the stable equilibria to do the work of increasing the Bass population while we were adjusting just the carbon input. Okay, let's take a look at question C. Here it says, suppose that it's hard for us to regulate fishing, and thus the exact density of bass. So there's the same assumption we had before. We don't have direct control over X, but we can control carbon inputs into the lake, so we have control of R again. If our goal is to preserve a density of at least 0.4, what should we do about the carbon input? Okay, so here we would like our bass population to stay around 0.4, which means we're looking at the range of R values. Let's make this question green. We're looking at the range of R values where there's a stable equilibrium around 0.4. So I think the part that seems most clear to me is right here, this big long section. So between about 10 and 40. So if I keep R in the range between 10 and 40, then small fluctuations to the Bass density around 0.4. Well, they'll keep us close enough into the 0.4, will not affect the long-term mass density. So this means that the mass density will stay stable around 0.4. Here in this system, as long as we're between 10 and 40 and we start out around 0.4, the mass population will always return to 0.4 if it drops lower, right? All of this is attracting. There's no other equilibria below the 0.4 equilibria. So we're always going to get back drawn up to 0.4. As well as long as we stay above the dashed red line, the population will always drop back down to the 0.4. So that's a pretty wide window. As long as x is between 0 and around 0.6-ish for most of that interval, it's always going to return to around 0.4. So here's just an example of how useful the bifurcation diagram can be. Once we have the bifurcation diagram, we could ask a lot of questions about how we can best optimize and manipulate our system to get certain behavior. Okay, so here's a review of bifurcation diagrams, a quick example, reviewing it using the Alley effect. We went over a new type of bifurcation called a pitchfork bifurcation that kind of shows up in these bandwagon opinion situations. And we gave an example of how we can use the bifurcation diagram in practice to model our behavior in adjusting a population. So if you have any questions about this, be sure to reach out to us on Piazza or in office hours. And take care.